Well, it's time for us to do some practice with problems involving related rates, and so that means we get to do a lot of word problems. So, woohoo! Bring in the word problems. It's going to be good. Now remember, it's important to be doers of the calculus problem and not just hearers only. So in other words, you need to be the one doing the practice. So don't just watch these videos, work the problems, and you can follow along with the videos. Use the pause button and say, okay, let me see what comes next, and try and do as much as you can on your own. The more that you do, the better you're going to become. Well, let's begin. So our first problem, you can see here, we have some blue water here. So let's see, what is it? A shark swims parallel to a shoreline, staying at a fixed distance of 3 kilometers from the shore. So it's moving on. Ba-dum, ba-dum, bum, 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 bum. All right. It is swimming at a constant speed of 8 kilometers per hour in the same direction as a lighthouse on the shoreline. See, they conveniently gave us a picture, which is great. Oftentimes we have to draw a picture. I will say I got really excited with coloring this blue. You could say I kind of blew it, but all right. Now, the question, at what rate is the distance to the lighthouse changing when it, being the shark, is exactly 5 kilometers from the lighthouse? And include units in your final answer. Okay, so we think about what's changing. Well, what's changing? Some things aren't changing. See, this distance here from the shoreline, that's not changing. That's fixed. Okay. This distance to the lighthouse, well, that will change. You see, by the time the shark gets over here, what's going to happen? Well, by the time the shark gets over here, it's going to be only 3 kilometers away. Currently, it's 5 kilometers away. So it's going to change the distance to the lighthouse. So that length varies. Well, what else? Well, we could say, what's another length? Well, this length is varying. Now, you might say, what length? Well, let's suppose we were to talk about this length here. We'll draw it on the shoreline. So in other words, it's the distance from the lighthouse to the nearest point on the shore, to the shark. Now you see, that's going to vary because as the shark swims along, it's changing. In fact, we can even read off how it's changing. It's changing at a rate 8 kilometers per hour. Okay, so we should give some labels. So let's see, we'll call this one, well, we can call it A, be anything we want. And this length here, we don't need to give that a name because this length isn't changing. So we're going to call it 3 because it's always 3. This length here, which is the distance from the shark to the lighthouse, is changing, so we'll give it a name C. So what's our relationships? Well, we have a right triangle, which is, of course, the best kind of triangle. So we get a squared plus 3 squared, which is 9, equals c squared. All right. So there's our relationship. Now, what do we know? Well, we know currently that c is equal to 5 because that's what we're told, but it's changing. So what else do we have? Well, this length is changing. So in other words, dA dt is changing at a rate of 8 kilometers per hour. But is it getting shorter at 8 kilometers per hour, or is it getting longer at 8 kilometers per hour? Well, see, it's moving closer to the lighthouse, which means that this distance is getting shorter. So that's a negative 8. Now, our units are kilometers per hour. It's very convenient not to write units during the computation. They will work out in the end to be what they need to be. All right. What else can we say? Well, we can use the fact that a squared plus 9 equals c squared and c equals 5 to say, hey, a squared plus 9 has to equal 25. Or we could say a squared equals 16, or a equals 4. Now, that means that at that particular moment, see, when we talk about related rates, we usually mean, well, at that one moment, what's happening? That's what's going to tell us our situation. Okay, So we have now information about C, the dA dt, and A. Well, the only thing we don't know is what's happening to C. What's the change? And that's what we want. If we knew that, we'd be done. So take our derivatives. 2a dA dt, the root of 9 is 0, is 2c dc dt. All right, good. Well, now what? Well, we can cancel the 2's right away, and then we put in what we know. A is 4, so 4 dA dt negative 8 is equal to C, which is 5, and then we have dc dt. All right, well, finally, dc dt is negative 32, which is 4 times minus 8, divided by 5. And there we go. Now we need units, but we can actually figure out units because we say, well, how are we measuring C? It's a distance, kilometers. How are we measuring T? Well, that comes from understanding that this is the dA/dt. So this unit downstairs, hours, that's how we're measuring T. So it's kilometers per hour. And there we go. And you might, if you were saying this out loud, say, we are decreasing at a rate, and you could be fancy and convert this. This is 6.4 of 6.4 kilometers per hour. And that's another way you could say this if you were speaking to someone who didn't like to have too many symbols and numbers. But, well, we don't have to spend too much time talking to those people. No. We like all people. We're very inclusive. All right, well, that was good. Nice, fun problem. Okay, well, don't worry, we have lots more. Let's keep going. So, you grab the water cup in the shape of a cone next to the water cooler to get a refreshing drink. After filling it up, you discover there's a hole in the bottom. Oh my gosh, you can see this is a very dire situation because there's even an exclamation mark here. So what happens? So a cone means that we have something that looks like this. And sometimes they made little tiny cups in the shape of a cone because it was very cheap. But they're really unwieldy. It's not a very comfortable cup to work with, but you have what you have. And so what does it say? Well, there's a hole in the bottom, which means, look, there's a hole down here. And so what happens? Well, if there's a hole in the bottom, it says that water's going to leak out. So your cup has some amount of water in it. I don't know. Say it's that much water. And then there's stuff dripping out the bottom. Okay, good. Now, what do we have? Well, let's see what we have. Now there's a lot of numbers, so we should start writing our numbers down. The cup is 4 inches high. So that's this length, 4 inches. And 3 inches across at the top. So that's the top, that's 3 inches. The water level is currently 2 inches. So this is the water level, and this part is changing. See, the 4 inches is fixed. That's inherent to the cup. It has nothing to do with the water. It's always going to be 4 inches up and down. This depth is changing. So let's give it a name. Let's call it H. And think of it as the height of the water. So what do we know? We know that our height is 2 inches. So H is 2 and is dropping at a rate of 1/2 inches per minute. So is dropping, that means it's going down. So we can say it's negative 1/2. Now I'm going to leave out our units for the time being, but we can see what our units are. We see that there's 4 inches, 3 inches, 2 inches. So our lengths are inches, and then inches per minute, so our time is minutes. So the question, how is the volume changing? Now, let's be careful here because there's a lot of words. You'll see So the fact that it says change, that's the derivative. So anytime you see something that says something is changing or what's the rate, these are all different ways to phrase it as I want a derivative. So what are we after? Well, we want to find, our goal is to find the change in volume over change in time, because we're looking for how is volume changing, and we're going to look at it and saying, well, what's changing we think of as, see, it's the change in our time. Okay, so that's what we want. All right, so that's going to be our answer. I don't know what it is yet, but look, I've already circled it. So whatever the answer is, it's going to go in there. So how do we get to our answer? Well, now we have this connection. And the connection is the volume of the cone. See, it tells us there's the volume of a cone is 1/3 pi r squared h. Well, that's great. That's beautiful. So we have volume is 1/3 pi r squared h. Now, what's changing? Well, volume is changing. That's the volume of the water. Okay? I guess I should say, when it says how is the volume, it's the volume of the water. So, the volume of the water is changing. The height of the water is changing. How about the radius? Well, when we talk about the radius for a cone, what's that referring to? If you were to draw a cone, the height is how far up and down you are. The radius is this distance. You can see if I were to let the water go way down, the radius would be very small compared to here, compared to if it were completely full. So the radius is changing as well. So we need to extract information about the radius. Now there's two things we can do. One is we could figure out what is dr dt and take a derivative, but we're going to go a slightly different route and say there should be a connection between radius and height. So we can kind of get a sense of it, right? Because if this were completely full, then our radius would be large, and if it's half full, our radius gets smaller, and if it's almost empty, the radius gets smaller as well. So that somehow the height and the radius should have a nice connection. So how do we get there? Well, here's sort of the idea. Look for similar triangles. Now this problem doesn't feel like a similar triangle problem, because when we think of similar triangle problems, we think of something two-dimensional. This is three-dimensional. So how do we get to similar triangles? Well, here's the case where we slice. So we're going to slice. And by that, I'm just going to take the cone, go straight down, and what I see is when I slice the cone, I see a triangle. This triangle right here. So, what am I after? Well, this is the cup. Here would be the water. I'll just sketch in the water. Now, I can see that the smaller triangle where the water sits would correspond to something similar to where the, just the whole volume of the cup. So, good. We're on track. We have some good relationships going here. Now, let's mark what we know in this diagram. We know this length up and down is 4. This length across is 3. The water level is h. How about this all the way across? Now, this is the important one. What is it? Is it r? No, it's not r. It's 2r. Because r, if you think about it, is coming from the center out. See, that's what r is. So if I'm going all the way across, it's like I went from the center out in both ways. So I get 2r. Now I can say, aha, I have these relationships. I can look at the ratios. So I can, for example, say 4:3 as, so that's the up and down, so that would be h, and then side to side, 2r. So 4:3 as h is to 2r. Now, if we move things around, so I'm going to solve for r. We can come to the conclusion, and I'll put it over here. So r would be equal to what? Well, multiply both sides by r, multiply both sides by 3/4. You get 3/8 times the height. So if I know the height of the water, how far up and down the water is, then I know the radius. Okay, so how do I use that? Well, what I can do is I can now take this information and plug it in to there. So we're going to update our volume. Well, so what is that going to become? We're now going to have that our volume is equal to 1/3 pi times 3/8 times h squared times h. So now what have we done? What we've done is reduced it down to two variables, v and h, where we know everything we need to know about h, and we're just after v. So if we clean that up a little bit, if we think about this, well, if I square 3, that'll give me 2 3s upstairs. There's 1 3 downstairs. So that'll leave me with a single 3 upstairs, pi h squared. Then downstairs, I canceled 1 3, 8 squared, 64. Okay, we're almost there. Now, what's next? Well, now take our derivatives and see what we get. So dv dt is equal to 3 pi over 64, that's a constant, times 2 times h times dh dt. Okay, so we're almost there. Why? Well, because we're looking for dv dt, we don't know that, but we do know h, it's 2, and we know dh dt is -1/2. Oh, whoops, I made a mistake here. Let me fix myself. Where was my mistake? Do you see it? Hey, that's an h squared. What should it have been? H squared times h is h cubed. Ah, see, that makes sense because a volume should have 3 measurements of length. So it would be really 3h squared. There we go. There we go. Now we're back on track. 3 comes down, h squared. Yeah, good, good. All right. So we know h is 2. The h dt is -1/2. So we can now put in what we know. So, we're running out of space. Well, that is a problem with word problems. Oftentimes there's just so much space to write stuff. We run out of space to do our computation. So, what do we have? We have dv dt is 3 pi over 64 times 3 times h squared, so 2 squared, times dh dt, which is -1/2. Now, the good news is we can clean up a lot. I can certainly see this 2 squared. I can cancel with the 2 there. Then I still have a 2 left. I'll cancel with the 2 downstairs. That makes a 32 downstairs. And what do we end up with? Well, there's a negative, which makes sense. Our volume should be going down because it's leaking out of the bottom. All right. 3 times 3 is 9. And then we have pi. And then we have a 32 downstairs. -9 pi over 32. Okay, so that's how the volume of the water is changing. Now, can we figure out our units? Well, our units of time, well, that's going to be in minutes, right? Because look, it's inches per minute. Now, how about units of volume? What is that going to be? Well, how do you find volume? You take your units of size, but it's a size times a size times a size, right? So it's inches cubed. So -9 pi, 30 seconds, inches cubed per minute. That's how much water is going to be dripping out of the bottom of our cup. Very annoying, very annoying. Well, we probably would go get another cup if we found a cup that was actually leaking. So, but all right, there you go. That's that problem. Okay, good. Well, on to the next problem. Okay. So, all right. Starfleet Intelligence has recently learned of a new Borg vessel that can change its shape, nicknamed the B-1000. The B-1000 has some limitations. Namely, it is always the shape of a box. So a box is just, you think of it It's not a cube. Cube is where all the lengths are equal, but it's, think of a shoebox kind of thing. And the volume is always 3,000 cubic meters. Currently, you only see two sides. The length is 12 meters and increasing at a rate of 1 meter per minute. The width is 25 meters and decreasing at a rate of 2 meters per minute. And then we need to figure out what's the depth and how fast is the depth changing. All right. Well, let's think about what to do. So what do we have? Well, we have our box. So we can draw ourselves a little picture here. So here we go. Here's our box. And we have 3 units of length. So they are what? They're the length, there's the width, there's the depth. So let's just say we'll call that the length, we'll call this the width, and we'll call that the depth. L, W, and D. That seems pretty reasonable. All right, good. Well, now what? We can say, hey, what's the volume? Well, to find the volume, that's pretty straightforward. And that is, volume is length times width times depth. And we're told something. The volume is always 3,000 cubic meters, which means the volume is fixed. It's not changing. So 3,000 is equal to length, width, depth, if we multiply them all together. All right, so there's our relationship. We found our relationship between our variables, length, width, and depth. So what are we after? Well, we're after depth and how fast it's changing. What do we have? We have our relationship, but what else do we have? So we have the length. We're told that is 12 meters and increasing at a rate of 1 meter per minute. So increasing at a rate, whenever you hear the word rate, think derivative. So the derivative of length with respect to time is 1. It's positive 1 because it's an increase. The width is 25 and it's decreasing. Okay, so what does that tell us? Well, the fact that it's decreasing tells us it's going down, so it's negative 2 meters per minute. Okay, now we need the depth. So what can we do? Well, first off, let's plug in what we have. So we have 3,000 is equal to 12 times 25 times the depth. Well, 12 times 25 is a nice number. It's 300. So if 3,000 is equal to 300 times d, then that tells us something. It tells us that d has to be 10. So there's our depth. We found our depth, 10 meters. Good. Now, what about dd dt? What is that? Well, let's take our derivative. Okay, so what do we have? We have length, width, depth all multiplying together. So what rule do we need to do to take the derivative? Well, we need to do the product rule. But here we have 3 pieces. So can we take the product when there's more than 2? Yeah, we can. In fact, we worked through it once as practice. And the way that the product rule works when there's multiple pieces is everybody gets a turn. And so we say, okay, just this piece changes, and then we hold the others constant. Then it's just this piece changes, hold the others constant. And then just this one changes and hold the others constant. So, taking our derivatives. Don't forget the derivative of 3,000. That's going to be 0. Equals, now we take the derivative of the first term. So dl dt, leave the others alone. Plus, leave the L and the D alone, and take the derivative of the middle term. dw dt. Plus, now leave the first 2 alone, L times W, take the derivative of the last term, dd dt. So that would be what would happen if we took the derivative. Now we plug in what we know. So we know 0 is equal to, well, what do we have? 1 times 25 times 10, because that's 1 times 25 times 10, plus then 12 times negative 2 times 10. Okay, plus, then we have 12 times 25 times, well, what we don't know. But that's okay, because we're trying to solve for that. So if we knew it, we wouldn't be doing this right now. All right, so what do we have? Well, we have 250. Then we have minus 24 times 10, which is minus 240. And 12 times 25, we've mentioned before, is 300. So dt. Well, this is pretty convenient. 250 minus 240, that's something we can actually do in our head. That's 10. Then we can move it across. So we now have negative 10 is equal to 300 times dt, or we could say dt is negative 10 over 300, which is the same as negative 1 over 30. Okay, so what's happening? Well, what's happening is that there is a change happening because it's something, but it's not changing by very much. It's changing very slowly. Now, is the depth increasing or is it decreasing? The answer is it's decreasing because it's a negative value. That indicates we're going down. Now, if we wanted to include units, it didn't ask us to. We could just say what they were. All our lengths have been measured in meters. Our per minute tells us that our units of our t is minutes. So our depth is 10 meters. Our change in our depth is negative 1/30 meters per minute. And there we go. There's our answer. Ah, what a fun problem. The Borg. Ah, the collective. Good times. Well, on to a different problem. So, to help eradicate the new invasive species, Algebraicus ridiculum. And you're probably thinking, yeah, I think some of the algebra is kind of ridiculum. But okay, what do we have? 4 boats set off from the center of a lake, each in one of the 4 cardinal directions, north, south, east, and west. There's a stretchable rig between the boats that makes sure to wipe out all the ridiculum inside the region enclosed by the rig, the shaded region. Oh, there's a picture that was, we ran out of space for the picture. Let me draw the picture really quick. So what do we have? So we have the center, and we have 4 boats. So there's a boat here heading north, and that we'll label A. There's a boat heading south, which we label B. There's a boat heading east, which we'll label C. And there's a boat heading west, which we'll label D. So what happens is here are our 4 boats. They're at the very end. And there's a net that goes in between. Now, the shape here is not going to be necessarily a nice shape. It's going to be some strange shape. It just depends on how far the boats have gone. So it could vary, of course. And if one boat goes very fast compared to the rest, it would make the shape much more lopsided. So it's not a square, it's not a rectangle. It's some sort of quadrilateral, 4-sided shape. All right, so suppose at a particular time we have the following. So the boat A, we know has gone 50 meters, and we know its speed. It's moving at 2 meters per minute. So this is 50, and it's going at 2 meters per minute. The boat heading south has gone 40, and it's moving at 3 meters per minute. The boat going to the east has gone 40, and it's moving at 1 meter per minute. And the boat heading west has gone 30, and it's moving at 4 meters per minute. So what we really have are lots of information about values of the location and values of the change. So we can translate this to say, look, A equals 50, comma, dA dt equals 2. Here we would say B equals 40, comma, dB dt equals 3. This would be C equals 40, comma, dC dt equals 1, and D equals 30, and the change in D with respect to T equals 4. And they're all positive. So all these derivatives are positive because they're all moving away. So the lengths are increasing, so positive derivatives. So the question becomes, well, what's happening to the total area which is enclosed by the rig? So, well, what is the total area? It actually gives it to us. It's 1/2 of A plus B times C plus D. All right. Now, even if they hadn't given us area, we could have actually found it without too much work, because we could say, well, look, there's really 4 right triangles. There's a right triangle there, there's a right triangle there, and so forth and so on. In each right triangle, the area is 1/2 base height. So this is, for example, 1/2 A times C. Here's 1/2 A times D, 1/2 B times D, 1/2 B times C. And if you put them all together, this is what you end up with. All right. And then, as a little bit of an added bonus, it says, make sure to include units for your final answer. Now, even without doing the problem, we know what the units are. Because look, we're looking for a change in area over change in time. That's what we're going to have when we talk about our derivative. So our area, because all our units are being measured in meters, so that would be, our units would be meters squared per minute. Okay, so that's what our units will be. So just at the end, we'll tack that on. All right, so, well, now we have to make a decision. What do we call our total area? Normally we would call area A, but we already have something that is called A, so we can't use A. So let's call it T, right, for total. All right, so we have our total area is 1/2 A plus B times C plus D. So now we have our relationship. They were kind of nice to us. They gave us the relationship. You know, it would be nice if all calculus problems were so easy, where they just like, and here's what you need, right here. Okay, well, let's take our derivative. So, taking the derivative, our derivative of area with respect to time, well, product rule. So we're going to take the derivative of the first, which would be dA dt plus dB dt times the second, C plus D. And then we're going to add to that the first, A plus B, times the derivative of the second, dC dt plus d dt. Okay, well, the good news is all of these little pieces, we know what they are, because that was what the problem gave us. So we can say that, lo and behold, dt dt is 1/2. Okay, so change in A with respect to t plus change in time with respect to t, so that's 2 plus 3. So that's 5. Times that by C plus D. So 40 plus 30. Well, that's 70. Plus 1/2. And now, A plus B, 50 plus 40, 90. And then, times that by the change in C and change in D, 1 plus 4, which is 5. Okay, good. Well, now what can we do? Well, actually, you notice something kind of convenient. See, these both have a half. They both have 5. So you could factor out 5 halves. Then you have times 70 plus 90. Well, 70 plus 90 is 160. So that's really 5 halves times 160. Well, 160 divided by 2 is 80. 80 times 5 is 400. So we get 400. Well, that's the rate at which the total area is changing. And of course, throw in your units, meters squared per minute. And there you go. That's the answer. There. Wow, nice. Clean answer. Isn't it great when the answers just come out and they're just like, wow, clean. Good. Well, farewell, Algebraicus Ridiculum. So, on to the next problem. A train is heading due east out of Conjunction Junction at a speed of 17 miles per hour and is currently 3 miles away. Okay, so maybe we should draw ourselves a picture. So, well, let's see, what do we have? We have Conjunction Junction and heading due east. So we're heading this direction. And so we're currently at 3 miles. So let's say we'll call this length, I don't know, I'll call it A. And we're told that A is equal to 3 miles, because it's currently 3 miles away. And the speed, well, that's information about the rate. That's a rate. So that's related to the derivative. Now, the thing about speed you have to be careful of is think about, do I need to make it positive or negative? Well, because I'm moving away, because I'm moving out. See, here's the clue. I'm moving out of. So that means I'm moving away from, which means my derivative should be a positive value. So dA dt is 17. Okay. Now, a second train is heading in the direction north, 30 degrees west. Okay. Well, let's figure out what that means. Now, that's a bearing. And so how does that work? Well, what you do is you say, all right, start by heading, not heading, I should say, but start by looking north. So I'm going to change my color for a second here just so I can get the picture right. So here's north. So this is north. And now what it says is start by facing in the north, and then we're going to turn 30 degrees in the westerly direction. See, there's two directions. I could turn east or I could turn west. And so we just have to make sure we turn the right way. So I'm going to turn 30 degrees towards the west. So what will happen is I'm going to end up pointing somewhere over here where this is 30 degrees towards the west, and therefore that is the second train. Okay, so here's our second train coming out in that direction. All right, so that's the direction it's going. What do we know about that train? Well, it's currently, I'll label that as B. We're told that it's also moving out. It's currently 5 miles away, so B equals 5. And the rate at which it's moving out, it's a positive value, is 19. So there we go. So there we know what's happening to these two trains in relationship to conjunction junction, which is represented as that single point. Okay, fantastic. Now, with all of that out of the way, what are we looking for? At what rate are the two trains moving apart from each other? So, in other words, the trains, we've talked about how they're moving relative to conjunction junction. The question is, how are they moving relative to each other? So we're after this side, we'll call it C. So we want to find, our goal is to find our DC dt. Okay, so that's what we're looking for. Can we do it? Now, you might notice something about this triangle. It's not the right kind of triangle. And so you might be thinking, well, what do we do? Because it's not a similar triangle problem because there aren't two triangles involved. There's just a single triangle. Well, it would be helpful if they gave us a hint. Oh, hey, look. They have something that right here. It might be useful to recall the law of cosines, which says, for a triangle with sides of length ABC and an angle theta opposite C, then C squared equals A squared plus B squared minus 2AB cosine theta. Oh, well here, look it up. We have A, B, C. Okay, good. And where's theta fit into this picture? Well, theta would be this angle here. Okay, so in our case, theta would be what? Theta should be 120 degrees because you have a 90-degree angle plus 30 degrees more. So we can say our relationship then becomes the following. Well, this is great news. C squared equals A squared plus B squared minus 2AB cosine of 120 degrees. All right. Now, you might be saying, hey, that kind of feels Pythagorean theorem-y like. Well, that's good. It should kind of feel Pythagorean theorem-y like, even though that's not really a phrase. Because what do you see? You see C squared equals A squared plus B squared. That is the Pythagorean theorem. Well, that would be if your angle is 90. And notice if cosine of 90 is 0. So in some sense, the law of cosine says, hey, here's sort of Pythagorean theorem if you don't have a right triangle. So, all right, what do we need? Well, it would be convenient if we knew what cosine of 120 degrees is. Now, this could be, maybe you might have a calculator available and it might tell you, or you have a lookup table, or maybe you taught trigonometry for 2 years. Well, that definitely helps. One of the best ways to learn trigonometry is to teach it for 2 years. And if you do that, you start to know these things pretty well. If you didn't know that, you could kind of start to reason what must be true. You could say, well, what's happening, if you think about your triangle, or rather unit circle, you have 120 degrees. That would be roughly over here. You're after knowing what's this x value, because the x value is the cosine. If you were to go straight across, that's like asking what's the negative of the x value for 60 degrees. Now, hopefully you know a couple of angles. Cosine of 60 is a half. So cosine of negative 120 is the negative of that. So it's negative a half. So what do we end up with? Well, we get the following. We get c squared is equal to a squared plus b squared minus 2 times minus a half is plus 1. So plus ab. There you go. All right. So there's our relationship. Now, we can actually use this to figure out something. So for example, we could now solve for c. So at our time, what would c need to be? Well, if we plug this in, we'll run the data through. So c squared would be a squared, 9, plus b squared, 25, plus a times b, which is 15. Well, 25 plus 15 is 40, plus 9 more equals 49. So what does that tell us about c? It tells us that our train is currently, or rather I should say our two trains, are currently 7 miles apart. Well, that would be great, but we don't want to know how far apart are the trains. We want to know how far are they moving, or rather, how fast are they moving? What's happening to that rate of change? The rate, see, that's the clue. The rate tells us we're after the derivative. So, there's just one last thing for us to figure out. dc dt. What does that equal? Well, let's figure it out. So, we know our road to take here. We're going to say, start by taking the derivative, clean it up, plug in what we know, solve what we don't. So, let's go for it. So, derivative with respect to t will be, here we'll have 2c dc dt equals 2a dA dt plus 2b dB dt plus, I'm running out of space, rather I should say dA dt times b plus a times dB dt. There we go. So we have to do the chain rule, then in the last terms we have to do product rule. So let's plug in everything that we know. 2 times c, well that's 2 times 7, that would be 14. So 14 times dc dt is equal to 2 times a, so that's 2 times a is 6 times dA dt, 17. 6 times 17 is 102. You can think of it as 6 times 10 is 60, 6 times 7 is 42, and you put them together, 102. Okay, then we have 2 times b, which is 10, times dB dt, which is 19. Well, thank goodness. 10 times 19 is really easy. That's 190. Plus, then we have our dA dt times b. So 17 times 5. Well, that would be 85. Okay, so plus 85. And then a times dB dt. Well, that would be plus 57. All right. Well, there we go. That's what it is, right? Well, what is that? Let's, I'm hopeful that they gave us some nice numbers. So we'll do a little bit of computation. So we have 102, 190, 85, 57. We'll add these up. 2 plus 5 plus 7 is 14. Carry the 1. 10, 18, 23, carry the 2, and 2, 3, 4, 434. Okay, so we now have that 14 times dc dt is equal to 434. Okay, good. Well, wait a second. I just want dc dt. I got to divide by 14. So, well, dc dt is 434 14ths. What do you think? Does 434, is that divisible by 14? Well, maybe. Actually, I think it is. Let's try it. So take 14, divide into 434. Well, I know that 14 doesn't go into 4. For 43, well, 43 is 42 plus 1. So, and 42 is 3 times 14. So it's really 3 goes there, subtract 42, remainder of 14, 1. So this is 31. Okay, so you can check it. You can check and see, lo and behold, it does indeed work. I know I was really quick there, but oftentimes if you had this kind of a question, I suspect this would be, we'll let you use a calculator on this one. So our final answer is dc dt is 31. All right, now if we wanted to throw units in there, what would be our units? It would be miles per hour, because our distances are all in miles. So you can see how it keeps talking about miles, and our time per hour, and per hour. So our time is measured in hours. And there you go. Wow, cool. We found it. Nice. And I think one thing that you should check is it reasonable? Now, I think it's right, so I do think it's reasonable. First off, it's positive. That's a good sign, because they should be moving closer. They are moving apart from each other, which means that the rate should be positive. But the other thing that you can see that shows you it's kind of a reasonable answer is think about what would happen if you were just going to add these two rates together, 17 and 19. Well, if you add them together, you get 36. Now, if they were heading exactly opposite each other, that would be moving at 36 miles per hour. We wouldn't even have to do any fancy calculus stuff. We'd say, oh, it's just 36. So we know exactly opposite. The answer should be 36. And that's as bad as it could be if you had two trains where one was traveling 17 and the other one was traveling 19. So our answer should be smaller than 36. So the fact that it's below 36 is a very, very good sign. So I think it's a reasonable answer. It's always nice to sort of stop and think about, is this reasonable? Good. Kind of a little bit of arithmetic work at the end. That's all right. We don't mind. Arithmetic is fun. All right. Good. Well, let's try another problem. So, a recipe for a cake includes strong baking soda, which causes the cake to expand. The cake always remains in the shape of a cylinder, where the height is 1/2 the length of the radius. All right, we can actually kind of get a picture of what that cake looks like. So we have the height is 1/2 the length of the radius. So if we think of our radius as being here, it's kind of a short cake. So this would be, the height would be 1/2 the radius. All right, so there's our cake. Now, as it expands, you are continually coating the surface with a special glaze. So you're able to keep track at the rate the surface area is changing. So because we're glazing, so where you can see, well, how much more glaze are we needing? Okay, so determine how fast the volume of the cake is changing with units. Oh, so we have units at the end. All right, well, that's fine. When the cake is 4 inches high, all right, that's some information for us to keep track of. And the surface area of the cake is expanding at a rate of 5/2 inches squared per minute. Now, the bottom of the cake is not glazed, so they gave us some information. The surface area is pi r squared plus 2 pi rh, and the volume is pi r squared h. All right. Now, we'll come back here and make a little note. Half the radius is the height. So, what do we have? Well, let's just throw in the fact that half the radius is the height. So the surface area, by the way, we can kind of see this makes sense. Pi r squared is the top of the cake. It's a circle. 2 pi rh is the side of the cake, and we're not doing anything about the bottom because you don't glaze the bottom of your cake. That's not how you make a cake. Now, let's replace h by a half r, since in our problem, h equals a half r. So our surface area would be pi r squared plus 2 pi r times 1/2 r. Well, what does this become? Well, 2 times a half is 1. So you have a pi r squared and another pi r squared. So that becomes, well, really, it's 2 pi r squared. All right, so that's our surface area. Now, what about volume? What is that? Well, the volume is equal to pi r squared times 1/2 r, because I'm replacing the height by 1/2 r. So this would become 1/2 pi r cubed. All right. Now, what do we know? We know the following information. So it's good to write down what we know. We know what? That the change in surface area with respect to time is 5/2. That's the information we're given. See, the surface area of the cake is expanding positive, so that's just telling us the sign, 5/2. Okay, what do we want? We want to know what is happening to the volume. So determine how fast the volume of the cake is changing, dV dt. So here's kind of the interesting thing. We do not currently have a formula that directly links surface area and volume. We could, in theory, get one. And why? Well, because what do we have? We have a formula that links surface area and radius, and then in the meantime, we have a formula that relates radius and volume. So we could manipulate and do that, but instead of doing that, what we'll do is we'll say, let's use our radius as an in-between, an emissary of sorts, so that we can say, hey, I know something about how the surface area is changing. Let me get that to figure out how the radius is changing. And then I say, hey, wait a second. I know how the radius is changing. Let's use that to figure out how the volume is changing. So we're going to sort of step our way towards it. So this is kind of the situation where we really have several relationships, so several formulas, and we're going to use all the formulas to sort of connect two of our variables together. So let's make some notes here. Now, the cake is 4 inches high. So our height is currently at 4. What does that tell us about our radius? So that's going to be an important piece of information. So half the radius is 4. So our radius would be equal to 8. Okay, excellent. Now, we have our pieces in place. So let's begin. So we'll start with our first equation with surface area. So we know the change in surface area with respect to time is equal to, take the derivative, 4 pi times r times dr dt, because the 2 comes down and then chain rule. All right, good. Now, what can we say? Well, let's plug in what we know. We know that this change, dA of surface area with the time, is 5/2 equals 4 pi times r, well, times 8 times dr dt. So what can we conclude? Well, we solve for dr dt. So dr dt would be equal to 5, and here, see, this is really 4 times 8, which is 32. Move it across, 5 over 64 pi. Okay, so now we have dr dt. All right, that's not what we're after, right? But it's going to help us to get to our goal. We're after how is our volume changing. This will be an important step. All right, now, next, let's start thinking about the other equation, which is the volume. Okay, so now we have to think about what's happening with our volume. So we're going to do something similar. So we have dv dt is, take our derivative, 3 comes down, 3 halves pi r squared dr dt. But now we know these things. Ah, good news. So this is 3 halves times pi. R is 8. So 8 squared. dr dt, that's right here. That's 5 over 64 pi. But now, look at some really cool stuff is about to happen. We're going to get a lot of nice simplifications going on. So the pi's cancel. 8 squared is 64. The 64's cancel. So what do we end up with? Well, we end up with a 3 and a 5 upstairs and a 2 downstairs. So 15 divided by 2, and that's it. That's our dv dt. It's amazing because you kind of anticipate there's a lot of pi's floating around in our formula for volume and surface area. So the fact that at the end there was no pi in the answer was probably not something we would have expected. Okay, but we can't finish yet because we really do want to get our units. And the reason we want to get our units is it actually asks us to get units with units, right? Okay, so we're going to get our units. So what will our units be? Well, we think of our units for volume. Now everything has been measured in inches, so volume would be inches cubed. What's our units for time? So how is time being measured? Well, it's being measured in minutes, so inches cubed per minute. And that's our answer. There you go. Nice. Good. Good times. Good times. Okay. All right. Our next problem. You are taking smartphone video of a race car from a position 100 feet from the track as shown in the diagram. So to be clear, this is where we're at in the diagram. So here is us taking our little smartphone video camera because we don't like to experience the event. We like to record it so that we can never watch it again. Okay, sorry, I digress. So the car is moving at a steady rate of 200 feet per second. That's pretty fast, but cars can go pretty fast these days. And the question is, how fast is the angle changing as the car passes directly in front of you? So the 200 feet per second says it's not speeding up or slowing down. It's always traveling at the same speed. And here's this angle. You're following along. And so we're asking the question, what's happening when the car is directly in front of us? So really, that's the question of when the car is over here. And it looks like this car is a little bit aerodynamic. Okay, so we really want to know what's happening at this point right here. So what are we after? Well, how fast is the angle changing? So that would be d theta dt. So that's what we want. This is what we want to find. All right. So now we think about our diagram. Well, what do we have? The nice thing is they gave us most of this problem. It's all laid out for us. We just have to put it all together. We have an angle. An adjacent side has been marked, and that's always fixed. We're staying 100 feet away. Then there's this opposite side, which is changing. And so since it's changing, let's give it a variable name. Let's call it x. And what do we know? Well, we know a couple of things. We know that the change in x with respect to time is always 200, and that's feet per second. Okay? It's a fixed speed. So it's always 200 feet per second, no matter what time we look at. Which time do we care about? We are interested in what happens when x is equal to 0, because that would be directly in front of us. See, that would be here. So this distance would be 0, and theta equals 0. So that's when we care. One last thing we need to figure out is what's the right relationship. So what connects this angle, this adjacent side, and this opposite side? Well, the answer is the tangent. Tangent is opposite over adjacent. So we can say tangent of theta is opposite over adjacent. Or if you like, we can say x is 100 tangent theta. I don't know if either one is better than the other, but there we go. Well, now we have what we're after, so let's take our derivatives. So, taking the derivative with respect to t, derivative of x with respect to t is 100 is a constant, derivative of tangent is secant squared times the derivative of the inside. Well, that's d theta dt. All right, well, we know what dx dt is. It's always 200. Okay, good. I guess I should have asked the question, can we say, is this 200 positive or negative? Well, in this diagram, what's happening is it's because I'm following as it comes in, it would be a negative. So I should update that. That should be a negative. All right, so what do we have? So we have negative 200. Here we have 100. And then we have to multiply it by secant squared of 0. Well, what's secant of 0? Secant of 0 is 1. So if you square that, you still get 1. So d theta dt. Now, divide by 100, we come to the conclusion that d theta dt is equal to negative 2. Now, we're done. We found the answer. If we were to phrase it as what are the units, what would they be? Can you see what the units would be? I think we all agree on the time. It's per second. What's the units in the numerator, though? Can you spot what they are? Okay, so here we go. The units in the numerator correspond to whatever the units of the theta is. So if we're talking about units of derivatives, you just say, okay, if it's d something over d something, you say, what are the units of the top? What are the units of the bottom? The top is theta, so we have to ask the question, what are the units of theta? So, what units are attached to theta? And the answer is, well, theta is an angle, and so it would be the measurement of an angle, which is radians. So, negative 2 radians per second. So it's not anything with feet. It's not a distance, it's an angle. You might say, how did we know it was radians and not degrees? Ooh, okay, that's a good question. Do you know the answer to that? I don't know if we actually ever explicitly said the answer to that. Okay, we're going to take a detour for a second here. Why does math always work in radians? When I say math, calculus. Why is it we always say, do radians, do radians, do radians? Don't do degrees, do radians. And, okay, so here we go. A little extra bonus. Since we got through this problem so quickly, I'll say why we know it's radians. You might recall a little fun fact where we said the limit as h went to 0 of sine of h over h is equal to 1. But what we didn't explicitly come out and say was this assumes that h is radians. All right. Now, why is that important? Well, could you have done it with degrees? And the answer is yes. You could have done it in degrees. You could have said, what does sine of h over h go to if h is in degrees? And what would it be? Sorry, I have to take a second here to think about this. So if I have degrees, this would go to pi over 180. Okay. Now, or it would go to 180 over pi. I can't remember. It's one of those two. I can't remember which one it is off the top of my head. Let's see, what would it be? Oh, I think it's, well, it's one of these two. Grab your calculator, try it out, and you'll see that it happens. Now you might say, where is this pi over 180 coming from? That's a conversion between degrees and radians. So, here's why we always work in radians. 1 is a nicer number than this value is. And the limit, that sine h over h, that shows up whenever you take the derivative of a trigonometric function. And we did take a derivative of a trigonometric function. See, we had a tangent. So whenever we're taking derivatives of trigonometric functions, if we want nice derivatives without these extra little converting factors showing up, we have to be assuming that we're in radians. So anyways, that's a little side note. And there we go. There we go. All right. Man, I apologize. I can't remember which one of those two it is, but it does go to one of those two, pi over 180 or 180 over pi. But all right, we've digressed. Back to the fun business. We're here to talk about related rates. Okay. So let's do another problem. So after a late night of deriving, your calculus instructor returns home. As they pull in, they see their partner, who is 5 feet tall. True story. My wife is 5 feet tall. She insists she's 5'1". The nurse says she's 4'11". So we're going to compromise and say she's 5 feet. Okay, anyways. Shh, don't tell my wife I said that. So, standing 12 feet in front of the wall, arms crossed and waiting to discuss the dishes situation. However, the calculus instructor is still thinking math, and they can't help but notice that as the car moves close, the shadow gets larger. Given that the headlights are 2 feet above the ground and currently 12 feet from their partner and moving closer at a rate of 3 feet per minute, then how quickly is the shadow of their partner moving up the wall? So, time to draw a picture. So, what do we have? So let's just go through and add this in. We'll now go through a second time. We see the partner, 5 feet tall. So we'll draw person, and here we go. We have that their arms are crossed. All right. And give them some legs. And we know that this is 5 feet. People don't grow that quickly, so that's going to be a fixed height. So that's good. They're standing 12 feet in front of the wall. Okay, so here, this will be our wall. And we know they're standing 12 feet in front of the wall. And that is also going to be fixed because they're standing. It's not like they're walking to the wall. They're running from the wall. They're just standing. Okay, so there's the car. Okay, so here we go. Here's our car. And not a very fancy car. If you're going to teach calculus, you have to take a bit of a vow of poverty. You probably didn't know that about your calculus instructors, but yep, they years ago when they were studying to become calculus instructors, they took their vow of poverty. So we have our car, and what do we have? Well, we have our headlights are on because, you know, we drive safely. All right. Now, what do we know about this car? Well, the headlights are 2 feet above the ground. So we should draw our ground in. So here is 2 feet to the headlight. And what else do we have? Currently it's 12 feet. So this distance is currently 12 feet. Now notice the word currently. See, the word currently is very suggestive in that it's indicative that something is changing. See, it's always 12 feet. It's currently 12 feet, so it's going to be changing. So since it's something which changes, let's give it a name. Let's call it x. So what do we know? We know x is 12. All right. And moving closer at a rate of 3 feet per minute. So that says that the change in x is dx dt. Closer means they're shrinking, so it's a negative value, and it's 3. Now, I want to point out here that you think this is very dangerous, but look at the rate. It's per minute. It's going to take us 4 minutes to get to the partner. So plenty of time. Mind you, we probably won't finish this problem in 4 minutes, but I think they would probably slow down. I'm really optimistic about that. So there's no imminent danger here. This is not they're flying through and they're about to, something terrible is about to happen. All right, so what's our last thing? Okay. How quickly is the shadow of their partner moving up the wall? Okay, so that's the thing we haven't quite put into our picture yet. See, what's happening is we have a shadow. So there's this shadow on the wall. And we're trying to answer the question of how quickly is the shadow moving up the wall. Now, what do we want to label the shadow? And I'm going to be careful here and say, I don't want to commit yet. Now you might say, why don't you want to commit? Well, secretly it's because I've done this problem before. But can we see what tool we need going forward? Whenever we see pictures like this, we should be thinking of similar triangles. And we should be looking for similar triangles. So we'd want to say, oh, there's a triangle here and the triangle there. But the problem is that this shadow, if we were to follow, say, from the wife, it doesn't cast it down through the floor. That just doesn't make any sense. So here's what we're going to do. We're actually going to do the following. So we're going to just take this 2 feet and go there. And now we have a nice pair of similar triangles. So 5 feet is the total height of our partner, but if we cut off the bottom 2, then it's really a 3 feet length here. Now, if I want to know how quickly the shadow is moving, I can do the same by figuring out what's happening to this length, because this bottom part is just always fixed at 2. All right. So the good news is, once you have the picture and you know what the right tool is, the rest of it's pretty straightforward, and you just have to be patient. So how do I mean by the rest of it's pretty straightforward? We know similar triangles is the name of this problem. So we think about what are our similar triangles? Well, we have this smaller triangle where the length from the light to our partner is x. The height of our partner is 3. So x is to 3 as, that means equal, this length, so from the light all the way to the wall, well, that's x plus 12. X plus 12 is to how high the shadow is, or at least this part of the shadow. So is to y. Okay, well, that's good. Well, in particular, we can do all sorts of things. So one thing we could do, we could actually solve for y. So let's do that, because we're really after understanding what y is. So we can rearrange this. We could say that y is equal to 3 over x times x plus 12. Now, if you distribute that through, what would we get? Well, we'd get that y is equal to 3 over x times x, which is 3, and then 3 over x times 12, which is 36 over x. All right. Well, and there you go. That's going to be what you get. Okay. Good. Good. Now you might ask the question, is this reasonable? So one thing you could think of is, what would happen, say, if x were very, very far away? So if x were large. Well, this would say that the height of your shadow should be 3. Does that make sense? Well, the answer is yes. You can imagine, for instance, take a very extreme case, which is to put the car out at the sun and have it shine, and then the light would be coming in parallel because it would have traveled so far. All the light comes in parallel, and then the shadow would be exactly the height of our partner, which means that this part would be 3. So yeah, that works. Good. And of course, if we had x being very small, x is 0, then you'd have a light source here, and the shadow would be gigantic, so it would be huge. So yeah, that's another good sign that it works. It's kind of fun to think about. Okay, now that I see the answer, can I see why this is a reasonable answer? Well, we're almost there. What's the last thing? Now that we have a relationship, what can we do? Well, take a derivative. So, taking our derivatives, what will we get? We'll get the following. So, derivative of y is dy dt is equal to derivative of 3, 0. Gone. Now, 36 over x. We should know that another way to write 36 over x, that's 36 times x to the negative 1 power. So, if we take the derivative, we'd bring the negative 1 down, so it'd be negative 36, x to the negative 2 power, and then times by dx dt. Or if you like, that's negative 36 over x squared times dx dt. So to finish up, we plug in what we know. Well, what do we know? We know x is 12, and we know dx dt is negative 3. So we have that dy dt is negative 36. Divide that by 12 squared. All right, that is 12 times 12 for right now, times dx dt, which is negative 3. Now, two negatives make a positive, which is good, because we think the shadow should be moving up the wall. So that means the derivative should be positive. That's a really great sign. 12 goes into 36, and that goes in 3 times. And then 12, this other 12 is really 3 times 4, and then I can cancel another 3. And therefore, we end up with 3/4. So what are our units? Well, our distances have been measured in feet, and our time is measured in minutes. So 3/4 feet per minute. Now, we could, of course, be wanting to confuse people and say, which is also 9 inches per minute. Well, because 3/4 of a foot is 9 inches. But of course, that's adding some extra confusion to it. And that gets into converting between different units, which is a different topic and not one that we're going to go into. But okay, there we go. Aha, good, good. Nice problem. All right. Our next problem. So, whoops, got to move it up so we can see the whole thing. So 2 jet aircraft are flying in opposite directions along straight, level, parallel, east-west flight paths that are 3 miles apart. So the distance between their 2 paths are 3 miles. So we have this person flying one way, that person flying the other way. Now, the pilot of the eastbound jet, so that's this jet, we'll make it this jet up here. So this pilot upstairs is doing what? Well, this is going at 480 miles per hour. All right. Now, the westbound jet is exactly 5 miles away from a straight line distance. So this is currently 5 miles. Now notice, currently. Why do we say currently? Because they're going to get close. Eventually they're going to be exactly 3 miles and then they're going to get farther away. Okay. And what are we told? The straight line distance between the 2 jets is decreasing at a rate of 640 miles per hour. So this is currently at negative 640 miles per hour. So the question is, what's the speed of this other jet? How fast is it going? And include units in our answer. Of course, the units are pretty much given to us. We can see what our units are. They're going to be miles per hour. All right, that's going to be straightforward. So the real trick is trying to figure out, how do we connect everything together? What's the glue that's going to make this all work in harmony? So let's think about it for a moment here. So what's the right picture? Well, we really see that there's a right triangle being formed here. We can throw in a little right angle here, and we say, all right, what can we say? Well, we have this side. We know what the current length is. We know how it's changing. And now the question is, that side is fixed, so let's label this side as A. We'll label this side as C. So we currently have the following pieces of information. We know that A squared plus 9 equals C squared. That's just Pythagorean theorem. Okay? We're told the following: C equals 5, and dc dt is equal to negative 640. Now, because we know C equals 5, we can actually get another piece of information for free. Plug in 5. What do you see? A squared plus 9 is 25. So we can say, aha, that tells us A squared equals 16, so A equals 4. So what can we find? Well, we can figure out what is our dA dt. So now we take our derivative. We're moving into we have our relationship. We've written down as much as we know. Now we're going to take our derivative and get a new relationship between the derivatives. So the derivative here, that would be 2a dA dt is equal to 2c dc dt. Now, the nice thing is we can cancel the 2's, so those are gone, and we plug in what we know. We know what A is 4. We know what C is, that's 5. And we know what dc dt is, that's negative 640. So, what do we have? Well, let's write it down. So, 4 dA dt is equal to, see, A is 4. 4 dA is equal to C times negative 640. Okay, well, divide both sides by 4. Now, if you take 640 divided by 4, that sounds complicated, but think of it, don't worry about think about a 64 divided by 4. Don't worry about the oidy. Because what we can do, 640 divided by 4 is really like 64 times 10 divided by 4. 64 divided by 4 is 16. So this is the same as 5 times minus 160, which is negative 800. Okay, so that says that the distance, this A is shrinking, is negative 800. So, is the westbound jet traveling at 800 miles per hour? And why not? Okay, the answer is no, it's not traveling at 800 miles per hour, but why not? Well, let's think about it for a second. So the issue here is that the change in A is being affected by both the jets. You see, it's not just the one jet down here which is changing A, but it's both jets. So what we see is we say, look, there's 480. That's the contribution from the jet we've already know about. So we need to combine that with this jet as well. So whatever the speed of this jet plus 480 has to get us to 800. So we take 800, subtract 480, and we come to the conclusion that the speed of the westbound jet is, dramatic pause as I grab a new color, speed will be 800 subtract 480, which is 320, and we'll throw in our units, miles per hour. And there we go. That's it. Wow, cool. See, so this is, you got to pay attention. You got to say, okay, because it's not just this one plane down here which is affecting A, but it's both planes simultaneously which are affecting A. All right, good problem. Aren't they all great problems? Wow, I don't know if we've met a not good problem yet. Well, it's calculus. All problems are fun. All right. So, while thinking about a question on your calculus final, that's a good thing. We should be thinking about problems. You begin rolling up your 8.5 by 11 inch exam long ways, forming an 11-inch tall cylinder. Okay, so now we say, all right, what do we have? We have a cylinder that we formed from our piece of paper. It's 11 inches tall. And then you let the exam uncurl so that the radius of the cylinder is increasing at a rate of 1/3 inches per second. So, okay, so we roll it up and then it slowly starts expanding again. Now the question is, at what rate, of course we see the word rate, think derivative, is the volume enclosed by the exam changing when the circumference is 6 inches? All right. So let's think about what we know. Well, first off, the volume is the volume of a cylinder. So we know the volume of a cylinder. So the volume of the cylinder is pi r squared h. So think of it as you take the area of a circle times it by the height. So what can we do here? Well, we know the height, it's 11. It's always fixed because the paper is not going to magically get longer. That's not how paper works. So we could really say, look, our volume is really 11 pi r squared. Okay, so that's our volume for a particular radius. Now, what else do we have? Well, we're told that the radius is increasing. Okay, so at a rate. So radius and rate, so that says change in radius over change in time. Increasing means positive, and 1/3. So that's the derivative of the radius with respect to time. 1/3 inches per second. Okay, so that's dr dt. And what do we want to find? Well, we want to find the rate of the volume. So find dv dt, and then there's a when. When the circumference is 6 inches. Now, what's the circumference? The circumference is all the way around a circle. So, if we use our formulas for circumference, the circumference of a circle is 2 pi times the radius. So, that should be equal to 6, or we could say we need the radius to be 6 over 2 pi. So we want to find dv dt when we have r equals 6 over 2 pi. So notice we have dr dt and r. We want to find dv dt. And finally we have this volume. We have all our pieces in place. So take the derivative. dv dt is 11 times pi. Take the derivative of r squared. 2 comes down. R, and then the chain rule says dr dt. So, plug in what we know. We have 11 times pi times 2 times r, which is 6 over 2 pi, times dr dt, which is 1/3. All right, now, hopefully, some things simplify. Well, yeah, 2 pi is pi times 2. 3 goes into 6. Leaves a remainder of 2. So what's left? It's actually kind of a nice number. It's 22. Now, what's our units? Well, all our measurements for distance are inches. So 22 inches cubed per time is second, because we see that per second. So that's how time works. And there we go. That's the answer. Great, great, good stuff. So, on to the next problem. Woohoo! More problems! Of course there's more problems. All right. So, there are 2 train cars moving apart from each other on a straight track. Now, the first car has a height of 3 feet and is moving left. Now, see, left is an orientation. So we left and right. So oftentimes when we think of moving left, we think of moving in the negative direction, and when we move right, think of it as positive. That's the natural orientation we assume, negative, positive. All right, so it's moving left at a rate of 8 feet per minute. So let's start drawing this picture, because we're going to have to draw a picture at some point. So we'll start adding things into our picture. So here we go. 2 train cars. Now, the first car, all right, it's a very short train car. So I'll just draw a little short one here. And we have that this is at 3 feet. And we know it's moving to the left, and it's going at 8 feet per minute. All right. There we go. The second car, it's a lot taller. It has a height of 12 feet and is moving right at a rate of 7 feet per minute. So it's, well, 4 times taller. Well, let's just say that's 4 times taller. Okay. And so this is 12 feet. And it's moving to the right here at 7 feet per minute. All right, good. Now, between the tops of the 2 cars is a cable, which is always kept taut. Taut is a fun word. It just means it's tight. There's no slack in the cable. Okay, so we draw in our cable. We'll just connect these 2 here. So here's our cable. You'll notice it goes from a height of 3 to a height of 12. So between the 2 cars, there's a device which is 9 feet tall, hanging from the cable. Okay, so here's our device. It's 9 feet. And it's designed to move to ensure it is just barely touching the ground. So, in other words, it might move to the right or it might move to the left. Now, it's always going to have a place to be, because I'm going from a height of 3 to a height of 12, and therefore, somewhere in between there's a height where I'm exactly 9. All right. Now, given that the 2 cars are currently 12 feet apart, okay, so, well, they haven't moved very much, so this is currently 12 feet. Determine whether this device is moving left or right, and determine the speed that is moving. So, who knows? It could be moving left. It could, in fact, be a trick question. Maybe it's not even moving at all. But the question is, for it to keep that right position, the question is, that ideal sweet spot, 9 feet exactly above the ground. Do I need to move left or right? Okay. Well, that's probably our first thought. Indeed. So, what can we do? Well, first off, let's try to get triangles into the picture. Now, one nice way to get a triangle into a picture is to sort of chop off and say the small height. So if I go through here and cut this here, then I could say, well, look, this is like now 0. This part would be at 6 feet. And then over here, this part would be at 9 feet. And the nice thing here is if I do that, now I have triangles which are similar. And that means I can apply the technology of similar triangles, which is a really good piece of technology to employ on these types of problems. So let's do that. Let's figure this out. Okay, so I'm going to redraw the picture just so I can have a better idea of what's going on. Now, the good news is certain things don't change. So this height of 6, that doesn't change. This height of 9, that doesn't change. This is based on the height of the device. This is based on the height of the second car, the second train car. What is changing are the distances here. So we have these distances. Now, what can we do? Well, let's label two distances. Let's talk about the distance from the left car to our device. We'll call that A. And then the distance between the two cars, we'll call that B. So, what can we now say with all of this in play? Well, we can now say the following. We have our ratios. A is to 6 as B is to 9. So that's good news for us. It's a really simple relationship. So this can help us. So in particular, if I know something about how B is changing, I can say something about how A is changing. So let's talk about how B is changing. So B is how far apart the cars are. Now, the answer to how far apart the cars are, well, it's currently 12, and we say, well, they're moving. See, they're both moving in different directions. So we say, well, if I want to know how quickly B is increasing, I say I look at this 8 feet per minute coming from the left, 7 feet per minute coming from the right. So I can say that the way that B is changing, dB dt, is equal to, and the answer is 15, right? Because we add 8 plus 7. All right, so now I can say, great. Multiply here. I'm going to clean up just a little bit before I take a derivative. So if I multiply by 6 and simplify, I get that the distance from A is 2/3 that of B. And that, seems fairly reasonable. If we think about, 9 is to 6, you would say, well, then you would expect a 3 to be here, and it seems it should be about 2/3 the way there. Okay. So our conclusion is then that taking the derivative, dA dt is 2/3 times dB dt, but we know what dB dt is. It's 15. So we have that dA dt is 2/3 of 15, which is 10. So that says this is going at 10 feet per minute. Now, how do we answer our question? Is it moving left or right? We understand now what's happening to the length from the car on the left to our device. This is going up at 10 feet per minute. So if we now combine the information here, the car on the left is moving in that direction 8 feet per minute. This distance is increasing at 10 feet per minute. So what's the net effect? Well, the only way that could happen is if what were true. Well, I need to have the device, this has to be moving to the right at 2 feet per minute. Because somehow I need to get that the movement of the device plus the movement of the car on the left has to combine together to get me 10 feet per minute. So our answer, are we moving left or right? We are moving right. So moving right, and we can say that our speed is at 2 feet per minute. And there we go. All right, good. In some sense, you look at it and say, the calculus part was pretty simple. It was the sort of understanding how to set it up. And even once you have the picture, there was sort of like an idea. It's like, okay, how do you find a similar triangle and then get the right ratios? The calculus is not the hard part about these problems. It's the setting it up. That's the challenging part. But the more that you do, the easier it gets. And I promise it gets easier. Keep doing the problems. You'll start saying, hey, there's certain patterns here. Hey, I can figure out how to make things work in a nice way. That's great. All right. Next problem. While studying for the calculus exam, some students take a break and bake brownies. All right, good. They stir the brownie batter in a bowl, which is a hemisphere with a radius of 5 inches. They then pour it into the only pan they have, which is a large circular cake pan. Okay, so that means a cylinder. And it's 12 inches in diameter and 2 inches deep. One student observes that the depth of the batter in the pan went up at a constant rate of 1/6 of an inch per second. Yeah, they've definitely been thinking a lot about rates. They must be in the first part of calculus when they're doing derivatives. Now, what's the problem? Find the rate at which the depth of the batter is falling in the mixing bowl when the depth of the batter in the mixing bowl is 3 inches. Okay, so here's sort of the picture to have in mind. So what we have is we have a mixing bowl that we're currently pouring. So it's sort of turned sideways, and it's a hemisphere, which means it's a half a sphere. And then below, we have a little cylinder here that we're currently filling up. So our brownie batter is filling up here, and then it's spilling in, and it's filling up down here. Okay, so that's our picture. That's our picture. And well, let's start putting things together. What do we have? Well, we need a lot of information here. So the batter in the bowl, it's a radius of 5 inches. Now that's useful information because I should have also pointed out there's a hint. The volume of batter of depth h in hemispherical bowl with radius r is pi r h squared minus 1/3 h cubed. Well, hey, we know this value for r. R is 5. Okay, so we can say that the volume of the bowl is equal to pi times 5 h squared minus 1/3 h cubed. Okay, now, what else do we have? Well, let's think about the volume of what? Well, we also have the volume of the pan. See, circular cake pan. And how do you find the volume of that? Well, that's going to be pi r squared h. Now, the circular cake pan, it's 12 inches in diameter. Now, if that means it's 12 inches from edge to edge, if I'm 12 inches from edge to edge, what's my radius? It's half of that. So my radius is 6. So this is equal to 36 pi h. Right? Pi r squared h, 36 pi h. Good. Now, I've now done something dangerous here, which is I've used h to represent the height in the bowl and h to represent the height in the pan. But they're different heights, so we need different symbols. So I'm going to be fancy here and turn this into a capital H. So capital H is what's happening in the pan. Little h is what's happening in the bowl. All right, now, so what's happening? Well, the bowl, the volume is decreasing, and then in the pan, the volume is increasing. But here's sort of the big aha. Suppose I add these two together. So the volume of the bowl plus the volume of the pan. What's true about that? Can you see? There's something nice about that. And you can you might say, I don't think there is something nice, but let me just make an argument here. When I look at this, let's just say the amount of batter that's hanging in the air, this is negligible. So we're not going to worry about that. Negligible. I think that's how you spell negligible. That's a very small amount. We're not going to take that into consideration. So when I talk about the volume of the bowl plus the volume in the pan, that's just how much batter there is. We're not creating batter by pouring from one container to the other. The amount of batter is always the same. So this is not going to change. It's a constant. Another way to think about that is that the amount of batter that leaves the bowl in terms of volume is equal to the amount of batter that comes into the pan in terms of volume. So that's another way to say that this is constant, that the inflow is equal to the outflow. All right, so take derivatives. And so we'll take the derivative of both sides. Derivative of the left-hand side, 0, is equal to, when we take the derivative here, we'll get pi times, 10h dh dt minus h squared dh dt. Then plus, here, we'll get 36 pi d capital H dt. Now the nice thing is we can do one cancellation immediately, free of charge. The pi's, woohoo, gone. Phew, done. Now, what do we know? Well, we have three things: d capital H dt, d little h dt, and h. So let's see what we know. So one student observed that the depth of the batter in the pan went up at a constant rate of 1/6 of an inch per second. That's this part right here. Constant rate, of course, that tells us it's a derivative. It went up, means it's positive. So this tells us that this is 1/6. So we know what d capital H dt is. All right, that's good news for us. And now we want to find the rate at which the depth of the batter is falling when the depth of the batter in the mixing bowl is 3 inches. So that tells us that our little h here is 3. So let's plug all that information in. So notice one other thing is I'm going to go ahead and just pull out dh dt. That's a common thing. So we get 0 is equal to 10 times 3, which is 30, minus 3 squared. So that's 30 minus 9, which is 21 dh dt, plus 36 times a 6, plus 6. Or we could say 21 dh dt is negative 6, or dh dt is negative 6 over 21, divide by 3, that's negative 2 over 7. So we can now say that the depth of the batter up in the bowl, that's our little h, that's the depth of the batter in the bowl, is negative 2/7, and we can even include units. Everything was measured in inches, and our time here was measured in seconds, inches per second. And there we go. That's our answer. Aha! Nice! So this is kind of interesting because we have two shapes. It's the idea of moving a quantity between the two different shapes. And so you can say, well, the total amount hasn't changed. So if you add the total volumes, then that's constant. You could have, like I said, well, look, let me compute the flow out. That has to match with the flow in. You'd get to the same conclusion at the end. All right. So, one more problem. I know we've done a lot, but I think one more, and we'll call it a good day. You have been hired as a lighting technician for a stage production of Calculus Review. You are in charge of a spotlight, which can only move up and down on a fixed pole to light the characters. At one moment during the show, the main character, D, played by an actress who is 5 feet tall, You might think, hey, didn't we have a 5-foot tall problem before? Well, it turns out 5 is a very convenient number, which happens to be a reasonable range for a height of people. All right, anyways, so D, our actress, 5 feet tall, will be 12 feet from the pole and moving away from the pole at a rate of 2 feet per second. The director has instructed you to light her in such a way that at that moment she will cast a 6-foot shadow and have the length of the shadow increasing at a rate of 2 feet per second. Determine the height of the spotlight and the rate at which the height will need to be changing at this moment. Include units. Wow, okay. I think we need a picture. So, what do we have? We have a pole. So here's our pole. And attached to this pole, we have this spotlight. Now this spotlight has the ability to move up and down. So here's our little light. Okay, so here's our little spotlight, and it's going to shine. All right, so we're going to add some light coming out here. All right, so there's our spotlight, lighting the show. Now, we have D. So let's draw D in here. So D is here. Here we go. Here's D. And delivering great lines as always. And what do we know about D? Well, currently we know that, well, let me put this up here a little bit. So we're told that D is 5 feet tall. So this is 5 feet. And yeah, that's not going to change. D is not going to grow during the show. She's 12 feet from the pole and moving away. So this distance here from D to the pole, it's going to change. So since it's something which can change, we give it a variable name. Let's call it A. I don't know. I'll call it A. Now, so what do we know? We know that A is equal to 12, because that's how far she is away from the pole, and moving away from the pole at a rate of 2 feet per second. So since she's moving away from the pole, that means the distance from the pole is increasing, so the derivative is positive. So dA dt is a positive 2. Good. Now, the director has instructed you to light her in such a way that at that moment she will cast a 6-foot shadow. So let's figure out the shadow. So then we come down here. So there's this shadow here, and the shadow is going to be 6 feet, and the length of the shadow is going to be increasing at a rate of 2 feet per second. So the shadow length is also changing. Since it's changing, we need to give it a name that's a changing kind of name. So we're going to call it B. So we're told B is equal to 6, and it needs to increase at a rate of 2 feet per second. So dB dt is equal to 2. All right, so we have all this wonderful information. Now, what are we after? We're after understanding the height of the spotlight. So we need to find the height of the spotlight and dH dt. All right, well, if you've made it this far, I think you see what we're going to be using to answer this question. We have a beautiful setup. It's perfect for us for similar triangles. And we can see it. So we have this larger triangle and this smaller triangle, and they're similar to each other. So our relationship tells us that the length of the shadow is to the height of our actress, B is to 5, as the length here from the shadow to the pole, which is the two lengths together, A plus B, is to the height H. So as that is to H. All right, or we could write this as B times H is equal to 5 times A plus B. So, well, let's find H. All right, let's see what we know. Well, we know a lot. We know b is 6, so 6 times h is equal to 5 times a plus b. Well, that's 12 plus 6. Well, 12 plus 6 is 18, but we're dividing by 6, so that's really going to become 3. So really, what does that conclude? That tells us that h is 15. So if you clean it all up, h is going to be 15. So we need h to be 15, and it says include units, so feet, 15 feet. All right, good. Now, we're not done because we also need to find dh dt. So for that, well, time to take a derivative. All right, so here we go. Let's grab another color here, and taking derivative. I'll take the derivative here. So product rule. So we're going to get change in b with respect to t times h plus b times change in h with respect to t is equal to 5 times change in a with respect to t plus change in b with respect to t. All right, so that's what we have. Now, plug in what we know. So dB dt is 2, h is 15, plus 6 times what we're trying to solve is equal to 5 times 2 plus 2. Okay. All right. So, well, that's 30 plus 6 dh dt is equal to, that'll be 20. Well, okay, 5 times 4. So subtract 30, 6 dh dt is negative 10, or dh dt is negative 10 over 6. All right, divide through by 2. That gets us to negative 5 over 3. So dh dt is negative 5 thirds. Negative 5 thirds what? Well, what are our units? Well, we have feet, and you can see our time, seconds. Feet per second. That's going to be going down pretty fast because, as she walks away, the shadow is going to lengthen, but we need to make sure to get the full effect, it needs to be going down. All right, well, there we go. We made it all the way to the end. A lot of problems. And you probably said, okay, we've done every single related rates problem that's ever been done. It kind of feels like that, but actually no. There's so many things you can do, so many variations. But there's lots of common themes. You've got your Pythagorean theorem, or in a pinch you could do law of cosines, which is a generalization. You've got your similar triangles. You've got your geometry. All sorts of fun, creative ways to come up and put things together. But the philosophies are the same. Look for the relationship, find it, and then take your derivative. Plug in what you know, solve for what you don't. And that's good. All right, thank you for hanging in there for so long. Hope you have a great day.